Okay, from this we can analyze the stability of the control system, okay, gain margin and the phase margin. Now this particular tool is called Bode plot. Okay, one question from Bode plot is always expected in GATE exam. Okay, a very important topic. Okay, now let's suppose I have some transfer function g of s k times s plus 1 upon s plus 2 s plus 3. Okay, for this g of s there will be some magnitude plot, there will be some magnitude function, okay, and some phase function. Both these are function of frequency. So whatever the plot, either so now for Bode plot it is further subdivided into two plots. One is magnitude plot and the one is phase plot. Now what is magnitude plot? On what scale it is plotted? Okay. Now see, the magnitude plot is nothing but the plot of 20 log 10 g of g omega versus logarithmic of frequency. Now question comes definitely to the mind that why logarithmic? Why not linear scale? Okay, because the variation with all linear scale are very wide. Okay, when omega is varied from 0 to infinity, the variations which are produced in magnitude plot and the phase plot are very wide. Okay, they have got very wide range. Thus to accommodate all those in this linear scale, it's not possible. That's why we go for logarithmic scale. Okay, where it is a logarithmic scale, these variations can be plotted easily rather than when we are in linear scale. That's why the x-axis is logarithmic scale and y-axis is 20 log of 10 g of g omega for magnitude plot. Again for the phase plot it is phase of g of g omega versus again the same logarithmic of frequency. So this was about the x-axis and y-axis of the plot. Now see the problem, gs equal to k times of s plus 1 upon s plus 2 into s plus 3 it is given. Now g of g omega I can write k times g omega plus 1 upon g omega plus 2 g omega plus 3. Okay, now to finding the magnitude of g of g omega, and 20 log of 10 times of g of g omega, it will be 20 log k times of under root of omega square plus 1 upon omega square plus 4 under root of omega square plus 9. Okay, now we can simplify this logarithmic expression. (20 log 10 k times under root of omega square plus 1 upon omega square plus 4 under root of omega square plus 9. Okay. This can be written as 20 log 10k plus 20 log 10 omega square plus 1 to the power 1 by 2 minus 20 log 10 omega square plus 4 to the power 1 by 2 minus 20 log omega square plus 9 to the power 1 by 2. Okay, I can still further write this expression as 20 log 10k plus 10 log 10 omega square plus 1 minus 10 log 10 omega square plus 4 minus 10 log 10 omega square plus 9. Okay. So this is the expression for 20 log 10 g of j omega. Okay. Now in this expression, this is my constant part. This varies with omega. This also varies with omega. This also varies with omega. Now I will plot all the expressions, complete expression on a graphical plot on y-axis and x-axis. That will be called my Bode plot or magnitude plot in with respect to Bode plot. Okay. Now there are certain rules for plotting this. Each of the factors k, s plus 1, s plus 2 and s plus 3, they have certain special plot. Okay. We will see first. Suppose first one, for plotting system gain k. System gain k can be plotted as 20 log 10 k dB. Thus, the point to be noted in this is, it is always constant. Okay. Its magnitude plot will be a straight line parallel to x-axis. Okay. For the value of k, whether k value is greater than 1 or whether k value is minus 1, third point will be, if k is greater than 1, then line parallel to x-axis lies above 0 dB point. Okay. In case if k value is lesser than 1, then line parallel to x-axis lies below 0 dB point. Okay. Where 0 dB point is when k value is equal to 1. When k value is equal to 1, logarithmic of 10, 1 is 0. So that will be my 0 dB line. Okay. This was one factor for system gain k. Second one will be, suppose if there are poles or zeros present at origin. In this case, the factor will be 1 by j omega or j omega. Okay. So for this, if I write the general formula for gain is 20 log 10 j omega to the power plus minus number of poles or zeros. Okay. So if number of poles is equal to 1, then in that case it will be 20 log 10 omega to the power minus 1 for poles. If it is 0, then it is 20 log 10 omega. Okay. So that's why if number of poles is 2, then it will become omega to the power minus 2. Okay. So now in this case, if I plot this, the rate of decrease in case of pole or the rate of increase in case of 0 will be minus plus p times 20 dB per decade. Okay. Suppose if there are 3 poles present, then rate of decrease of the slope is 3 into minus 3 into minus 20, which is equal to minus 60 dB per decade. This is for 3 poles. Suppose if there are 3 zeros, then 3 into 20 is equal to 60 dB per decade. At that time it will be increasing slope, and if poles is there, it will be a decreasing slope. Okay. Now, how to see? If suppose, point to note in this is the starting slope of the body plot. Okay, will decide the number of poles or zeros at origin. It is the starting slope which will decide this. Okay, this is the second part for the poles or zeros at origin. Third case will be when there are simple poles or zeros. Simple pole means it's a pole of first order. Just like 1 plus j omega t plus minus n, where n is the order of simple poles. Okay, I should write here, suppose simple pole of order 1, then n value is equal to 1. So 1 plus j omega t plus minus 1. In this case, what will happen? See, if I see the magnitude plot, the magnitude in dB can be written as minus 20 log of under root of 1 plus omega square t square. Okay. For low frequency range, omega value is lesser than 1 by t. In this case, it will be 0 dB. For high frequency range, again the different thing will be there. For high frequency, omega value greater than 1 by t. In this case, magnitude in dB is equal to minus 20 plus minus 20 log omega t. Okay, this will be a straight line with slope plus or minus 20 dB per decade. Okay, now initially if I plot 1 by j omega t plus 1, let's suppose this is, I want to plot this, then in this case the body plot will be something like this. This is my 1 by t point. From here to here this is 0 dB. At this point it will start decreasing at a rate of minus 20 dB per decade. Okay, suppose in case if it is a pole, if it is a 0, then it is g of j omega equal to j omega t plus 1. Then in that case it will be like this. This is 1 by t, 20 dB per decade, 0 dB. Okay, simple, because in this case it will magnitude will be 20 log of omega square t square plus 1 to the power 1 by 2. Under approximation I can draw it like this. Okay, suppose g of j omega is a pole of order m. In that case, if I want to plot, this is my 0 dB, the point of 1 by t will be like this. After that it will start decreasing at a rate of minus m into 20 dB per decade. Earlier it was only minus 20 dB per decade, now it is minus m into 20 dB per decade. Okay, the rate of decrease of slope is high. Similarly, for if it is a 0 of order m, this is increasing at m into 20 dB per decade. Okay, so simple. So we have taken the first case when there are simple zeros. Now suppose there are quadratic factors. In this case, my g of s, h of s will be 1 by 1 plus 2 zeta omega n s plus s square plus omega n square. Okay, so I can write the magnitude of this minus 20 log under root of 1 minus omega by omega n whole square plus 4 zeta square omega by omega n whole square dB. Okay, this is the magnitude of this. Now definitely for lower frequency there will be an approximation, and for higher frequency there will be different types of approximation. Approximation and quadratic factor. Okay, the first one, for low frequency, omega lesser than omega n, omega by omega n whole square is lesser than 1. In that case, magnitude in dB is equal to minus 20 log 1, which is equal to 0 dB. What will happen is 1 minus omega by omega n whole square plus 4 zeta square omega by omega n whole square. Okay, this term is already lesser than 1, so this term will be 1 square plus this term again lesser than 1, so overall this term will become much more lesser than 1, it will 4 zeta square omega by omega n square, which is equivalent to 1, because zeta value is already less than 1, omega by omega n is much lesser than 1, so it is 1. So minus 20 log 1 is 0 dB. This was the first approximation. Second one is for higher frequency. Omega greater than omega n. Now omega by omega n is much greater than 1. Okay, so 4 zeta square omega by omega n whole square is much lesser than omega by omega n to the power 4, because as zeta is, now in this case magnitude in dB is equal to minus 40 log omega plus 40 log omega n. Okay, so these were the few approximation and the few different types of factors involved in plotting the Bode plot. Now we will see certain examples which will clear more concept about the Bode plot. Okay, so this is a, now we will use these techniques in plotting the Bode plot also. Problems. First one is, okay, the transfer function of a system is given. K is lesser than 1 by t. Okay, plot Bode plot for this function. Transfer function is given. Now in this transfer function there is one constant variable k, one pole of first order and one pole at origin. Okay, and it is also given that k is lesser than 1 by t. Now since pole is present at origin, so definitely the initial slope of this function is going to be minus 20 dB per decade because the pole is of single order. Now write down first point, since pole is at origin, thus slope will be minus 20 dB per decade initially. Okay, one more pole is added at minus 1 by t. Thus since already the slope is minus 20 dB per decade, and if pole is, one more pole is added to that, the slope will become minus 40 dB per decade. Let's see this. Twenty log k minus 20 log of j omega minus 20 log of j omega t plus 1. Okay, so this is my function. For smaller values of omega, now if I this is my 0 dB point. Okay, g of j omega at omega equal to 1 by t. Let's suppose that 1 by t point is somewhere here. Okay, since t value is also not known. At omega equal to 1 by t, I have two terms, 20 log k minus 20 log of omega. I can ignore this term for the time being. So this will be 1 by t. So this is 20 log k minus 20 log of 1 by t. Okay, so this will become 20 log of kt. Now initially one condition is given that k is lesser than 1 by t. This also means that kt is lesser than 1. That means at omega equal to 1 by t, 20 log kt is lesser than 0 dB. Okay, so while plotting at 1 by t, my point will be somewhere here. and will start with a slope of minus 20 dB per decade. Minus 20 dB per decade. At omega equal to 1 by t, one more pole is added. This pole will change the slope from minus 20 to minus 40 dB per decade. Okay, this way this body plot is plotted. One more problem. In this problem, magnitude plot of a body plot is given, and we have to find certain values. Okay. dB omega 1. 26 dB. This is increasing at a rate of 20 dB per decade. Then it is decreasing at a rate of minus 20 dB per decade. This frequency is omega 2. Find omega 1 and omega 2. Okay. To solve this, we should know one more thing. 20 dB per decade is equal to 6 dB per octave. Decade is change by a factor of 10. Octave is change by a factor of 2. Thus 20 dB per decade means 20 dB per change in frequency of by factor of 10 is equal to 6 dB change if a frequency changes by a factor of 2. Now looking at the graph, from here to here there is a change of 6 dB. Okay, so once there is a change of 6 dB, that means the slope of this line, which is 20 dB per decade, is equivalent to 6 dB per octave. From 20 dB it changes to 26 dB. That means change is equal to 6 dB. So if frequency, if it is 10, then omega 1 will be 2 into 10, which is equal to 20. Okay, radians per second. Now after reaching at 26 dB, it has come down to 0 dB. Okay, coming down from 26 to 0 dB, there is a change of 26 dB. So from omega 1 and omega 2, they will be related by something. Okay, let's suppose in between there is some frequency omega 2 dash. Omega 2 dash will be nothing but 20 into 2, which is equal to 40 radians per second. Okay. Now from 20 dB, again the slope is again minus 20 dB per decade. Omega 2 will be 10 into omega 2, which is equal to 400 radians per second. Okay. So this is a solution. This is the value of omega 1 and omega 2. So the important point to know in this is 20 dB per decade is also equal to 6 dB per octave. Once if we know this relation, we can easily find the solution. One more problem. In this, a Bode plot is given and we find the transfer function. Six dB. This is at 0.1, set omega 1. Minus 20 dB per decade. Omega 2 constant, and again at 10. This slope is minus 20 dB per decade. This slope is minus 40 dB per decade. Okay, for this we have to find the transfer function. From 32 dB, it has come down to 6 dB and then become constant. Okay, that means change is equal to 26 dB. So 20 dB change means change in frequency by 10, because it is decreasing at a rate of minus 20 dB per decade. Omega 1 will be 0.1 into 10 into 2, which is equal to 2 radians per second. At omega 1, 0 is present. Okay. At omega 1, there is a 0. So this 0 will make my slope as 0 dB. 0 dB. That's why 0 dB per decade. That's why it is a straight line from omega 1 to omega 2. Next, that means there is a pole at omega 1 equal to 2 radians per second. Next, between omega 2 and 10, the slope is minus 20 dB per decade. Okay, so the value I know is minus 6. For finding the value of k, again which is a constant, I can write 20 log k is equal to 6 plus 20 log 2. Okay, then with this I can find the value of k. 20 log k is equal to 12 implies k value is equal to 4. Okay, I got 1 0. One pole is already there. One pole is at origin, because initial slope is minus 20 dB per decade. Initial slope is equal to minus 20 dB per decade. Thus, one pole at origin. Next, to find omega 2. From 6 dB, it becomes 0 dB at a rate decreasing minus 20 dB per decade. Okay, thus omega 2 value will be 10 by 2, which is equal to 5 radians per second. At 10 there is again one more pole which is making my slope minus 40 dB per decade. Okay, thus by knowing the value of omega 1, omega 2 and omega 3, I can easily find my transfer function. 4 times of s plus 2 upon s into s plus 5 s plus 10. Thus there are 3 poles and 1 0. That's why the final slope will be 3 into minus 20 minus plus 20 dB. So final slope is minus 40 dB per decade. So this was one of the typical problem which can be asked in GATE exam. Okay. So this initially completes the topic of plotting the Bode plot, in which we have plotted the magnitude plot. Okay. The phase plot is generally useful while finding the phase margin and gain margin of the system using Bode plot. Otherwise, if a question comes in the exam, it will be mostly on the magnitude plot, okay, or magnitude frequency response.